Hey, hi guys. It's Wednesday, April 22nd. You're not going to be having class with me on Thursday or Friday. Thursday, you're supposed to take an ACT practice test and with Miss Ferguson. And on Friday, we don't have school from here on out. Okay. Uh, I'd like for you to look at page 555. There's something I forgot to tell you. And you can see the orange statement there. All reactions are reversible under certain conditions. Well, those are closed reactions. Take a look at the test tube in the picture on 555. They have some mercury oxide there. They're heating it up with a flame. It is forming mercury and oxygen gas, and it's got a stopper on the top that you cannot see in the picture. So once the mercury, and once the oxygen is formed, what happens is it recombines with the mercury to make mercury oxide, and then it breaks down again. And then that particular temperature and then the pressure inside the system, inside the vessel, it allows it to go back and forth. In fact, it says here under the orange sentence there, it says theoretically every reaction can proceed in two directions, forward and reverse under suitable conditions. Now, I'd like to say that would be in a closed vessel. Okay, I'm on page 556. Another thing I didn't describe to you are equations that are reversible, that are in equilibrium. They'll either lie to the right or they will lie to the left. And the example that they gave there was sulfur dioxide plus oxygen yields sulfur trioxide. And so you got balanced equation. It looks like it's going to be 2, 1, 2. All right. Now it's a reversible reaction. And what it does is it lies to the right. So if you take a look on page 556 at the top, you will see that the arrow on the top is bigger and the arrow on the bottom where it's reversing is smaller. And we always read from left to right. So we say that this lies to the right. And those arrows are not talking about the rate at which the reaction is proceeding right or proceeding left. The rate is the same. Left, whether it's going towards the left or whether it's going towards the right. That's why we call it equilibrium. We're saying that this is a closed system of constant pressure and temperature in a vessel, a reaction vessel. So the rate is the same going to the right or to the left. But the thing that's different that we kind of imply in those arrows is quantity. So the product quantity is greater. Quantity. Than the reactant quantity. I'm going to go ahead and kind of like put some numbers to it. These are theoretical, hypothetical numbers. Let's suppose at the beginning we have 10 grams of this. And we have 10 grams of this. And we have no grams of that because we just got started. And as the reaction proceeds, it uses up these reactants. Now we're down to 2 grams of this and 2 grams of that. Go to make 4. Take 4 away from 20 and you're going to get 16. And so the situation at the beginning is this, and at equilibrium, the situation is that you got a bigger amount of product and a small amount of the reactants. So when you consider the quantity of the two, there's greater quantity of product and a smaller quantity of reactant. Even though there's some coming back to the left and replenishing the reactant, it's not all that much. Okay? So that is what they're talking about. And they say that this reaction will lie to the right. This reaction lies to the right. What that means is once equilibrium sets up, there's a greater quantity of product than there is of the reactants. And then one that would lie to the left, kind of like, suppose this right here, we're ionizing. And you know, as soon as you get a little bit of ionization done, like 3%, it reverses on itself and goes back to molecular form. And when it goes back to molecular form, that's about 97% of what's in there. There's only like 3% ions in that vessel. And so it would lie to the left. It would be going back to molecular form and not driving to the right. Okay, those are terms that are going to be floated around in your college chemistry classroom, so I wanted you to know them. On page 557, I gave you the equation for the equilibrium constant. And on page 559, there is a table there that shows the equilibrium constant is the same regardless of the initial concentration of the reactants. The thing is, you got to keep it at the constant temperature and pressure. And you can see that this is an elevated temperature of 425 degrees Celsius. I'm looking at figure 1.4, where the constant is 54, and it has no units. That's by convention, no units. So those are big K values, big equilibrium constant values. What does that mean? That means the equation lies to the right. That means you're getting a lot of product. So when you have a big K value, the industry is really happy. And it's all about making money. So if you're making this product, which in this particular example on page 559 is the product hydrogen iodide, and you're making it at a rate where the equilibrium constant is 54, you're making a lot of money because you're making a lot of product for the company. All right, but let's do another one and let's plug some numbers in there. I'm on 560, sample problem A. 560 sample problem A. Let's do that numerically. And they say an equilibrium measure of N2, O2, and NO gases. What's the equilibrium constant for this system? So we're taking nitrogen and combining it with oxygen. We're taking nitrogen and combining it with oxygen to form a closed vessel there, so its equilibrium sets up, and none of it escapes. 2NO. Gases. 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 Gases at the temperature at which this is taking place. And it does not tell you what that temperature is. So, so they're all gases. So we're taking 2 moles of gases and making 2 moles of gases in this case. So it isn't affecting driving to the right or driving better to the left. If there are more, well, we'll talk about that in a minute. So what is the equilibrium expression? Well, that's easy. It's products over reactants. So it's NO, concentration of NO, nitrogen monoxide, squared. You see that too? And it's divided by the product of the reactants, product of the concentration of the reactants to the first power, times the concentration of oxygen to the first power, And now we're going to plug in some values, and we're going to get that equilibrium constant. 1.1 times 10 to the negative 5 is the concentration of that product NO. And down here, we've got 6.4 times 10 to the negative 3. And the oxygen was 1.7 times 10 to the negative 3. And by the way, this is molarity. Those brackets mean moles per liter, or molarity. So the implication is these are solution reactions. The stuff has been dissolved in water. Okay, and so they react, and the value of K, let's look at the bottom here, 1.1 times 10 to the negative 5. No units. 0.4 zeros and a 1. Question: is that a little number when you compare it like to the previous problem with 54? Yeah, that's a little number. So which way is this going to lie? It's going to lie to the left. So that arrow to the right would look like this. So what does that mean? That means you're not making very much money for the company because it's remaining as reactants. And it's not making a lot of product. So how do you solve this problem? The way you solve this problem is maybe you change the temperature, and maybe that'll make it drive to the right. Now we're going to talk about the Bosch deal over here. Okay, I'm on page 562. This is really critical. This is the equation that we're going to deal with. Nitrogen plus hydrogen. This was nitrogen and oxygen. We're going to go to nitrogen plus hydrogen. Yields ammonia. All right, and the it's 1, 3, and 2. And the nitrogen, they're all gases. They're gases at the temperature in which this thing is running. And the pressure for that matter. Okay, I'm on page 562. I wonder how long I've run. I really want to teach you this. Critical. I don't know. So let's go ahead and give it a swing. You know, like right around the 1900s, there was a crisis in the world. It's called the nitrogen problem. And few living organisms can utilize the gas that we have in our air, which is nitrogen, 80% and 78%. 4 out of every pieces of air. Take a piece of air that big, chop it into 5 pieces. One of those pieces will be oxygen, the other 4 will be nitrogen, and all the other gases in the atmosphere is less than 1% of the air we breathe. And so 80% basically of the air we breathe is nitrogen. But it does not get into the roots of the plants. It's got to be in compound form like this is right here, ammonia, before the plants can suck it up. It's got to be what they call fixed. And the only place in the world that had a whole bunch of fixed nitrogen, that is in compound form, was down in Chile, where they had this stuff called saltpeter, and it was sodium nitrate. Yeah, but they felt like the rest of the world was going to starve because they couldn't fertilize their plants, and therefore they were not going to have enough to eat. And so it was called the nitrogen problem. They had to find a way of producing, synthesizing ammonia, of producing artificially through chemistry ammonia, and they had to take hydrogen and nitrogen gas to put them together. But they had to use a catalyst. It was pure iron, and they had to elevate the temperatures up to about 1,000 degrees Celsius. And they had to use 200 atmospheres of pressure. And once they did, and the guy that discovered this process is a German physicist, a chemist rather, named Haber. And the industry that put his discoveries to work was headed by a guy named Bosch. He was an engineer for BASF. I think it was a German company in like the early 1900s. And so we called it the Bosch-Haber process, and or the Haber-Bosch process. You can see an industrial plant on this 563, the picture there. And so now we've gotten that up to not 1,000 degrees Celsius, but like 500 degrees Celsius and 700 atmospheres of pressure. I mean, it's really high temp, really high pressure, but it's not too high of a temp, but it's just right. So this will run at around 500 Celsius and at about 700 atmospheres of pressure in order to make this thing run. Now, why do they have greater pressure? Well, the reason that they have greater pressure, by the way, that solved the world's problem of starvation. Artificially manufacturing the ammonia. All right, so if you have 4 moles of gas as reactants and you squeeze on it, which way is it going to pop? It's going to pop to the right. It's kind of like when you have that great big zit, you know, and you squeeze on it, which way is it going to pop? Into the mirror. And so if you can go ahead and put the stress on there of high pressure in the reaction vessel, we call it a stress, like a great big old ugly zit that's red and inflamed. And if you put high pressure on that, it's going to burst in that direction. Okay, that's nice. And then the second thing you're going to do is you're going to suction this off. As it's produced, you're going to suction off the gaseous ammonia. And so in those two things, it's going to drive greatly towards the right. It's going to be predominantly towards the right. We're not going to have much coming back to the left at all. And this company's going to make lots of money. And the reason is because high pressure stress is going to pop that direction. And you're suctioning off the ammonia. So it's like you've got a vacuum over here. When you suction it off, it's like a vacuum. What happens when you take a straw and you suck the air out of it? Doesn't that create a vacuum where the fluid in the glass comes right up the straw? Well, it's going to draw that to the right. So there's one reason that it draws to the right, it's the high pressure. The other reason is because there's like a vacuum. After they make the product, they're going to suction that off of the reaction vessel as it's produced. And so that's the Bosch-Haber process that I wanted to tell you about. If you look on 564, you can shift equilibrium by changing pressure, which I just discussed. More moles of gas on the left as reactants. So if you put pressure on it, it's going to pop to the right. And then changing the concentrations, you can affect the equilibrium constant and drive more directly to the right, or, you know, more product. And page 566, you can change the temperature, as we were talking about here. This reaction that I have on the board releases 92 kilojoules. So another product is 92 kilojoules of heat. is a product. So if it's exothermic, you don't want to get it too hot, because if you get it too hot, what's that going to do? You know, they initially ran it at like 1,000 degrees, and they backed off to like 500 degrees Celsius. And the reason they had to back off is because that made this really big. So if you add heat, because you're in greater temperature, that's going to cause it to want to drive back to the left, which is counterproductive. So the temperature had to be just right, because this is an exothermic process. See ya.